That's like 5 grand. And you just know how to make that deal on top of it.
All right, everyone, let's go ahead and get this party started. Someone said class is like a film party. What's that?
Plain don't lie.
All right, everyone, so welcome back, whatever. Since we definitely had a no-show Friday, I got a lot of things to return, so it's just your past homework and test for some of you. Going off on a new subject today, I'll upload, sorry, I was a little late with last lecture, that's uploaded. Oh, and I sent you an email, I screwed up question 7 on the homework. Instead of referring to question 5, I referred to question 6, which was just a screw up, so I changed the numbers. Again, it was a little equation that you have to show. Well, here, let me remind you what it is. I don't even know where this is in my notes. We're going off in a completely different direction. I don't even know where my notes are. This is really stupid. How did we even talk about this time? I remember. So last time we talked about how to get, don't draw this, you don't need to draw this. Just to remind you what we did last time, and unfortunately I don't recall where my notes this is, because we're in a very different place. But what I showed you last time was, given that you have a starting point, which I always make a triple point, you can define the lines for solid liquid. And remember that this ends up being divided by the change in volume. The liquid is a minus the solid. And so that's why water slopes left and most things slope to the right. Just remind you of that. Remember, most things expand when they melt, and water doesn't. So that's unusual. Now remember that we also made an approximation for the volume. We made an approximation for the volume such that the solid gas and liquid gas were slightly different. We plugged in P equals nRT, and we get a very exponential type of rise for that and that. And of course, this comes to an end. It's not part of the equation. Just draw it like that. And solid, liquid, gas, of course, crystal. So anyway, I just had some very simple equations. And what you often do is, again, this is a very traditional way. I can't remember the equations. But what you can do is you can manipulate them once you have the delta H's and the triple point. You can always put them into this form. It's some number minus some other number over t. Over t. And the trick there is, so again, sorry, for a given temperature, what's the pressure for the liquid gas or the solid gas, which would be sublimation? So take the equation, plug in numbers, and you can traditionally get it in this form, and that's what I got wrong on number 7. I wrote out, I used the wrong numbers. So anyway, that's the answer to that one. And so the calendar, I need to upload the calendar because we're doing a lot of really different things. We're going to do colligative properties today. It is really painful. So you brought your chin sticks, right? So today of all days, if you fall asleep, I'm okay with that. Normally I don't like that, but this will be a little bit boring. Then we're going to spend the next 2 days on multi-component phase diagrams. I know you engineers have already had that, sorry. And then after that, we're out of material because I was double checking over the weekend. I have covered everything that anyone who takes PChem 1 will cover. So there's really nothing in the book I have. So now I hope you realize you get the same level of information as Harvard and Caltech and MIT. Oh, did that thing just do something? Is that thing still recording?
Yeah, it did stop. Yeah, it froze. Wait, no, never mind. Sorry.
Okay. I thought I heard it one of your smartphones anyway. Thought I heard it beep, but actually it's not true. You don't get the same level of information as Harvard or Northwestern. You get more. You do. They actually only teach, I'm not kidding, they only teach 13 weeks. Most schools only have semesters of 13 weeks. We have 15. So that's a really good thing, right? So that's, I would really hate to shoot 2 weeks off. And actually, I can say this because this dean is gone, but we had a dean 4 or 5 years ago who said, he sent this email to all the faculty, all the LAS faculty, and he said,
I'm not going to cut the semester. And we're like, yeah, you're going to cut the semester. Especially when you start out that way. You know that that's what he's actually trying to do. So I'm not going to cut the semester, but I want to have the last 2 days, Thursday, Friday, Tuesday, how it is. I want to have the last 2 days off for reading day so they get to study, more time to study for finals. And the thing, I know that sounds nice, but that was a slippery slope. That was going to be, that year, he had to get us to vote on it, which we 100% voted no. It was going to be reading day that year, and the next year it was just going to be cut. And then what that does is it saves money, because in my salary and lecture, especially lecturers, your salary goes down. So I certainly didn't want to see that happen. All right, so I could have some motivation. But also, I really think this class should be 15 weeks. It's a real screw over to cut it down to 13. And that's just a money grab, by the way, folks. That's just them taking your money, right? You just have a longer Christmas break. I know that sounds nice, but it's not ultimately good for you. So remember, I told you this at the very beginning. Personal trainer that doesn't push you is someone you ought to fire. All right, so long story short, what the hell am I going to do? I'm going to go off the book. In fact, so we normally teach this as a 3-semester class, 342, 346, 344. And 344 was mandatory for many years. Then we were not allowed to do that because it could force people to take over 120 hours. We're not allowed to do that. So it became optional. It was one of the three, you have to have those 3 electives. Well, 1 elective of 3 choices, now you have only 1 choice. What happened was no one was signing up for 444. And because of budget cuts that we know are coming, we have to have 10 undergrads in the class when the class is canceled. There was no way we were going to hit that number, so 444 got canceled. So what am I going to do with my last 3 days?
444.
444. Oh, you know what? If you said cancel class, I would have done it. But now you want to I just messed with you. We'll go over some 444 stuff. I will provide citations. I'm just going to use a different book. I don't know that you have access. You can torrent anything, right? But I will provide references. But you know how I do this. I can get it across that you don't need. You don't really need the book. I don't know how many of you are even reading still. So I will provide references, but I'm just going to go over everything in class that I want you to go over. And the thing that was really a shame about 444, as you're going to see, what I'm going to do is cover shape, group theory, because you're not going to get it any other place. You get a little bit of it in inorganic, but PChem we do some different things with it. The thing about group theory is it's non-mathematical. It kind of is mathematical. But you do things on charts. And it's this really clever little, it's like a crossword puzzle. It's relatively easy. There really is no substantial math involved whatsoever. So here's the trick. 444 was actually always easier than 346. So you guys should have signed up for it. It was an easy A. And there's almost no math in it. But it's too late. They've already canceled it. So that's a shame. Unless you guys want to work together and petition to get it back. You engineers, you're not required to take it. So of course, you're not going to do it. But you chemists, if you can get 10 of you together to say we'll take 444, which is easy, we might be able to bring it back, but we have to know that we have 10 people. So I can't tell you to do that, but please do it. It'd be awesome if you did. Okay, well, I'm just running my mouth because I don't have a lot to talk about. Today, again, we're doing related. Properties. Okay, calm down, folks. I know it's Monday, or radio on Monday. Okay, colligative properties are what happen when you add salt to water. Now, you had, in freshman, I know you covered this in freshman, you're given the equations for like freezing point depression, and then you plug in numbers, and then that's good enough. I'm going to derive those equations. But now, here's the thing. I should have really done this after Rayleigh's law. You're going to see Rayleigh's law over and over and over again. It's just that this material is so old and inexact that I hate it. We are going to make substantial approximations that almost invalidate the results. And on your homework, again, it's on your homework, so I have to get through this. Also, there's not much to ask you to do with colligative properties. I'm going to do the derivations. And I hate them because of the approximations I have to make, so I don't like even doing them. Leaving me with I don't have derivational questions to ask you in terms of colligative properties on the third test or the final. Those will just be straight up number questions, and you're good with your calculators. So these are freebies, all right? But just understand that there's a really lot of approximations, and the approximations get so bad sometimes that the results are just almost meaningless. Okay, in terms of Caligula properties, what happens when you add salt to water? Okay, let me turn, I was running vapor pressure. Sorry, that's an awful thing, guys. Vapor pressure, okay, goes down. I'll just write it that way. Now that would be of the solvent, so you might want to write that down. I'm not going to put that down, just hope you know that. Now again, this is another solvent, freezing temperature goes down. Of course, you are aware of that. Let's see, boiling point goes up. Why am I spelling boiling? Boiling temperature goes up. And of course, that's why you want to add salt to water if you live in Denver, which is way high up in Mexico City, because of the vapor pressure and lower altitude naturally being lower means that water boils at a lower temperature, so this is how you can raise it back up. Now here's one that's a little funky. I'm not going to talk about it too much. Osmotic pressure. Osmotic pressure goes up. And that's relevant to cells. If you put cells in a solution that doesn't have the right kinds of ions, so that's one way to culture cells. So you may think of culturing cells in a petri dish, but you can actually do it in a homogeneous solution. As long as there's the right salts and stuff to eat in the solution, and if you get that wrong, the cells either like literally wither away and die, or they explode. So, and that's due to osmotic pressure. I'm not going to say too much about that because this isn't PTF for biochemists. You can speak a little bit more about it, and that's actually what I'm doing next semester, if you're wondering. Then here's the trick. All right, I'm going to have this on the test, all right? Anyway, there's got to be something on the test. And maybe I'll just ask you to name these things, right? Now, here's how you remember it. In case you get confused at all, draw your regular phase diagram. And again, the solid region goes on for very, very long ways. What happens is it's as though these two lines here, so again, that is salt to water, these two lines just do this. All right, so that's how you can remember it. So now, let's look for every effect. Okay, so boiling point. Instead of boiling here, we now boil here. Right? So the boiling point has gone up. Okay, melting, or the opposite of fusion, instead of occurring here, now occurs there at a lower temperature. All right, so we melt at lower temperatures. Right. Vapor pressure. Sorry, I did it that way. Instead of having this vapor pressure, instead you have this vapor pressure. So vapor pressure went down. Osmotic pressure, if I ask what are the four things that have occlusive properties, I'm not saying I will, so I haven't really decided yet, because again, I don't know this material too much. This gives you three of them. Hell, maybe I'll even ask you just to draw this, because that gets the point across anyway. Okay, so now again, when you were freshmen, you had all these equations for boiling point elevation and freezing point depression. Where did they come from? Since I know it's easy to not question things, especially when you're 18, but those equations came from somewhere, and they came from largely Raven's law. And so for solvents, so I'll do, what am I going to do? Boiling point elevation and freezing point depression is the exact same thing essentially, with one slight twist that I'll go over. Okay, so now remember that, so again, Raven's law, you know I'm going to be doing chemical potentials. Okay, so I have a material, I've got delta G in the table in the back of the book, and it's a liquid, but remember Raven's law, it's not nRT, I've got RT, again, because this is chemical potential. And again, Raven's law says that LN, sorry about that. RT, remember, this is an entropic thing. That's the entropy of mixing times temperature gives me energy. And R gives me the right units, and N is gone because this is chemical potential. Okay, so note that this is the liquid, and remember that if you have salt in water, and another thing about this, I'm going to invoke this in 1 second, you're going to assume that the salt is very, very low. So that's part of one of the approximations I'll make. So if the salt content is very low, then Rabel's law is actually pretty good. That's the only time any of that, Rabel's law, Henry's law, it's the only time any of it's any good, is when you're talking about a solvent with a very small amount of the solute. Then it's okay. Okay, and then, since I'm going to do boiling point, I want to think about the gas. So, of course, in equilibrium, we would be equal to that of the gas. And this would be, again, for, here, I need to add a little label here, sorry about that. If you didn't add it, don't worry about it. So, I'll call it species A, because I got B and A. A will be the liquid, B will be the salt. Okay, so again, not too terrible. This is the colligative properties. This is one of the better ones. The approximations aren't nearly as bad. Now what I've got is an RT, LN, mole fraction is the difference in the gas, pure chemical potential, A, because B will come up in a second, versus the number in the back of the book, or A for the liquid state. And then I've got, okay, pathetic derivation, I'm just going to divide by RT. I shouldn't be rewritten it. Hurts my wrist. Minus the same, the pure chemical potential of the liquid, for A over RT. Okay, because this is such a simple derivation, let me just go ahead and do the next step. Where this is just, what is that? That's the delta G of vaporization, delta G per mole. A per mole over RT. Oh, I'm sorry, it needs a little, sorry, I'm not following IUPAC. Delta VAP. Sorry, I'm already kind of small today. Over RT. Okay, one more step. So again, remember the tables in the back of the book are very easy to follow because they're all per mole, which makes them delta G and chemical potential simultaneously. So that's kind of nice. Now, here's the thing. Again, this is the mole fraction of water. And the way we like to think about these, just as normal human behavior, is that you don't add water to salt, you add salt to water. So we like to think of mole fractions of not of the solid, but of the solute. So I'm going to take this guy and take ln 1 minus, and again, make a note so you don't get lost that B is the salt. So, sorry, I'm writing kind of small today, I'm a little bit bigger. Okay, now an approximation I'm going to make is that I'm going to say that ln 1 minus chi B is minus ln chi B. So that's coming up, and that's because chi B is considered very small. Okay, now this is where this gets a little funky. I want to see how the boiling temperature changes. So what I'm going to do is take the derivative of this guy with respect to temperature, then bring over the dt and do an integral. So that's the idea. So when I do this, when I say, what's the change in ln B with respect to temperature, says that, and this will be boiling temperature, says that because this thing's changing, this thing's changing. And that's actually true. So it's not too terrible, it's just a little odd looking. And yeah. So then I've got 1 over R, change with respect to temperature, delta VAP G per mole of A. Sorry if I put it wrong. All right, yeah, not good board work. All right, remember Gibbs, Helmholtz, that's right, Gibbs-Helmholtz equation. Change in G over T. Remember, this has come up over and over and over again. And of course, this is going to be 1 over R. Where did my notes? 1 over R
minus the enthalpy, right, not the G, the enthalpy over T squared. So, sorry, this is a little odd.
Okay, now trick is bring the T over here and integrate both sides. And, yeah, not too fast. Okay, so big ol' therefore. I'm gonna separate. Okay, everyone, I hear you. Try to read. Equal to, okay, now of course limits are always an issue. Okay, now this is kind of funny. How do you get the limits? And what I do, one thing I do like about this is that this is one of those times I can write an equation and tell you about the action that is the same thing as solving the equation itself. So now the lower limit is water before I added salt, and the upper limit will be when I added the salt. Okay, so natural log, if there's no salt, then this is the natural log of 1, which is 0. Meaning it's just not there, right? Isn't that nice? You know, we've got a definite interval, but one of the limits just isn't there, so it goes away. In this guy, and again, remember that there has to be, the limits have to be used for partial, again, always comes up, and I've added a certain kind, so now it's real. I don't know what it is, I haven't decided yet, but whatever. Okay, now, the temperature is going to be the lower form. Remember, these got to make sense together. So what temperature is that? If I haven't added any salt, remember I'm doing boiling point elevation, so this is the standard temperature. It would be the boiling temperature. And then this T2 on top is the new boiling temperature. Okay, now in terms of bringing DT over here and doing these integrals, nothing wrong. Nothing wrong with that. That works. What doesn't work is, if you look this up, what are you going to find? What temperature is this for?
Standard.
Huh? One person say, oh, that's a cat. Yeah, that's standard temperature. If you look this up, if you look up the enthalpy of vaporization, you will almost always find it for whatever at 298.15. But now, take water. It's not, it doesn't boil at 298.15, it's 373.15, right? 100. And so that means that I'm using the wrong delta H vaporization. As the temperature changes, so does that. So remember, this guy's a function of temperature. So I need to include that into here, but we don't. We just assume that it's constant, which is pretty off, actually. Not terribly off. This is one of the ones that work better. When we do changes in solubility and temperature, that one is horrendously bad. But again, another approximation is that if you look these numbers up, you're going to be using the 298 temperature. Either you've got to figure out what the real delta H is, and of course with heat capacities, or you're just making a mistake. And you really ought to include the temperature dependence if you really want to do it right, but we're not. And again, remember this side is me adding salt starting from nothing. Okay, so this guy is really easy. This is just going to be ln 1 minus chi b. Room. And 1 over, integral of 1 over x squared is, well, you can do it in your head, it's not hard. The derivative of what is 1 over x squared. All right, the derivative of what is 1 over x squared? Well, I think I heard minus x to the minus 1, that's right. So that makes us positive. Okay, again, forgetting all the fact that this is wrong. R, and then I've got 1 over x, and I've got 2 limits, 1 over T2 minus 1 over the boiling temperature. Okay. sorry, I didn't use the board too well, and I'll just continue downward. I was always tempted to start like on the board on the left, but I found that it wouldn't work. Okay, the next step, again, so I made one approximation, that's not so great, but it's only one approximation, but now, really bad approximations start kicking in. Number one is, okay, approximation number one, ln 1 minus chi b is sort of equal to minus ln chi b. And again, this assumes that chi b is relatively small. And that was one of the stipulations for these derivations, is that you added salt, but not a hell of a lot. And that's really generally not true, especially obviously when you're pulling this stuff all over the road, just like that with potholes. So approximation number one, I didn't add much salt. And this is not such a terrible approximation if this is really a small number. And you hopefully have seen this at some point. This is pretty vigorously true. If this is really small, then this actually works really quite well. Okay, so now what I'm going to do is I have, wait. No, sorry. Yeah, no, geez. Sorry, folks, sorry. What is wrong with me? I knew something was wrong. Sorry. Just chi b. My bad. So, I'm a little off today. If you're not sure about this, just try plugging some numbers in the calculator, and you'll see how close it really is. Sorry about that, I had to spell out. Okay, so therefore, chi b, notice I didn't write minus chi b, I'm going to fix that. Sorry, I'm going to make certain you know this is an approximation. So I'm going to eat up that minus sign in a different way, and I'm going to do that here. Remember T-Boyle. See, I switched them. Okay, so that's where the minus sign went. Okay, and now what I'm going to do is set this equal to delta that. What we're going to do is simplify this, and it turns out that this is the same thing as T2 minus T-Boyle over T2 times T-Boyle. And just simplify that and see that these are the same thing. So didn't have to do an approximation here. Okay. Now approximation number two, E2 is roughly equal to T-Boyle. Did I say number two. Sorry. Number two. Okay, if that's the case, here I'll put down chi b again, is delta t. Okay, so we're going to call that delta t. Okay, here's my enthalpy times delta t. So that's your change in boiling temperature. So the T-Boyle squared, so which is like R, T-Boyle squared. Okay, now what you really want to solve for is delta t. And that is, therefore, chi b T-Boyle squared times R over the vaporization enthalpy. Sorry, no way. There you go. It's dying on me. Okay, so not much to this. Right? You see, I don't have much to work with. I can't really change this derivation anyway. I don't know that I care to. I don't think I can plug in Van der Waals equation for P equals nRT. It never showed up. So you can see that I don't have a lot to work with in terms of derivations. So don't. It's complicated enough, especially because you have to insert approximations. I'm not going to ask you to just like redo it on the test 3. That'd just be kind of a trivial waste of time. I think you get lost, especially on the approximations. So there you go. If I have a question, I'll have maybe like one question of this nature. It's just going to be a calculator one. Another neat thing to look out for is, notice that I'm having positive. So this positive delta t is, that's definitely like how much higher the temperature went because you added salt. But now let me point out to you though, freezing point depression. A freezing point depression does the same thing. Sorry, I've painted myself into a corner. Freezing point depression is going to be done the exact same way, so there's no point in doing it. So for freezing, okay, again, freezing point depression, delta T is going to, again, be how much salt you added. It's going to be the freezing temperature squared times R over, remember that liquid turning solid is technically called fusion, so FUS. And you want to make sure that you get the notation right. Like I said, the mole too, whatever. Okay, now this one's a little trickier. Technically, so you're going to get a positive number here. Don't forget that that is how much it drops. You really ought to be getting a negative number. We really ought to put a minus sign in front of there. So you really ought to get a negative number, but it's just not expressed that way. It's a positive number, but it's just how much your temperature went down. And so that's in your homework as well. So you do saturated, which again is wrong. You look at saturated water and you see how much the freezing point depression is. And again, it's not too far off. These guys work better than what I'm about to go into, which is solubility as a function of temperature. So again, not much to do with this, just it'll be on the cheat sheet, you'll plug in numbers. I just gave you 3 points, that's awesome, all right? But again, the approximations are really quite severe. Okay, let me leave that up here, and now solubility changes. And this is where it gets really nuts. The solubility changes with temperature. Okay, there is one good thing about this, is that it shows you what types of things influence solubility. And that's, that's some physical insight. But under extreme conditions, the derivation is insane. It just doesn't make any sense. Okay, so here's what it's talking about. Again, one of the hardest things about this next part is understanding what the heck it is I'm trying to do. What I'm trying to do, again, is I'm going to see how solubility of something, what the solubility of something is, and I'll do that as a function of temperature. And so, again, I'm going to have to connect the liquids and solids chemical potential. And so this is for the liquid. And how about, let me just drop the A and B label for now. It just adds complication that's unnecessary. This will all be for B. Again, this is the salt in the water. And again, this is the number in the back of the book. And I'm automatically diluting stuff, so I better add RTLM. And again, I'm talking about the salt in the liquid. Now, that of the solid, right, because I have to connect these two together, is again the solid NaCl in the back of the book. Star again means the pure substance. I said this a long time ago. I said it a long time ago, and I mentioned that it was a setup for what I'm doing today. And that is that the activity of a solid is 1. And I'm not even talking activities. So whether you think of activities of a solid as being 1, or its mole fraction within the solid phase is 1, either way, this term is 0. So it goes to 0. Sorry, let me do it this way. Sorry, that may be confusing on your notes. I don't want to confuse you when you look at your notes later and get confused because it's something weird. So that ends up being 0. And again, that is, because solids are pure. Okay, let me get a new pen. This thing's dead. Okay, so now I've got to connect these two together. Oh, and by the way, I didn't do this, did I? One reason that when I was doing the previous derivation, when I had the gas chemical potential, there wasn't an RTLM mole fraction because, again, you assume that the solid has no basic pressure. Sorry, I should have mentioned that before. Yeah, where am I at? Notes. Okay, so now I'll set these two to equal. So again, this will be in equilibrium. Because, yeah, if you think about it, this part does make sense. I'm adding salt to water. It dissolves. That means the chemical potential of the ions, the liquidy salt, is lower than that of the solid. And that's going to keep happening as I scoop and scoop and scoop. And you can roughly, it's somewhere between 25 and 30% of water's weight is the amount of salt you can add before you hit saturation. So I know that I hit saturation because the chemical potentials of the salt crystals and the ions in solution are now equal. So there's no drive to dissolve anymore. So that's why I'm setting these equal. And that automatically means that I can chuck this stuff in, but it's not going to dissolve. So again, kind of a similar derivation. And since I'm not looking at the vapor pressure of the solvent, I'm looking at the solute, then I automatically have this, my salt, again, my salt is B. Okay, so then, like last time, I subtract the chemical potentials. How about I just go ahead and divide by RT? And let me just go ahead and say, okay, a little funky. Fusion is the opposite of this, of solids melting. So when I plug in delta G of fusion, I actually have to put a minus sign because, again, I'm describing the opposite of what IUPAC has defined fusion to be. Per mole, because it's chemical potential. They're the same thing. And then that is Ln. Kind of B. Okay, so now what I'm going to do, so I've pretty much actually defined it, but what I want to do is look at temperature variation because, long story, this temperature is actually defined like it was last time. Last time it's boiling temperature. At this time, this temperature is actually the melting temperature of salt in this case, which is pretty freaking high. So what I want to do is not try to solve that at that temperature. I want to solve at a lower temperature. So I do the same kind of wacky trick, do the derivative with respect to temperature, and 1 over R. Let me just do it like this, over T. I'm just skipping all the labels because otherwise we're going to have a little. So this will be, so remember this is going to be minus delta H over T squared. So I've already got a minus sign, so this is where you get one little difference. The minus sign has gone away. Okay, so there's that. Okay, now I'm going to bring this sucker over here, and this is the integrals. Change it to Ln chi B. And again, understanding understanding this guy for sorry, I'm missing a little bit there. It doesn't matter. Just per mole. Squared T. Okay, so again, limits. This one's a little harder to understand the limits. What we're going to do is talk about the solid dissolving. So now, initially, the solid has a mole fraction of 1, meaning the lower limit is, again, wiped out for a different reason. Again, that's because I've chucked some salt in and it didn't dissolve, so it's all still there. But I know that at some point it won't be. So it will dissolve, giving me a certain mole fraction, which I can take the natural log of, is just another number. So that's why that works the way it does. Now this is technically going to be, okay, again, now I'm going to make a terrible approximation. I'm going to say that if this stuff retains its solidity, that means that it's right at its fusion temperature. So the temperature at which the liquid turns to a solid. Now that automatically means that if I'm at the fusion temperature, if I go above it, and my salt melts, it means it's automatically mixing with the water. That's not necessarily true. I mean, what if this isn't salt? It's, oh, I'm missing an R there. So, no, it's right out here, sorry. My bad. And then this will be a lower temperature. So, again, the approximation here, this is what I really don't like because it's all because of these limits. The idea here is, again, that if the thing is right up to its fusion temperature, it will retain its solidity. It won't dissolve, and that's wrong, all right? And anyway, so that's where this really gets kind of nutty. Now, there's not much to do with this. I'll toss this up here in a second. So again, the one thing that is of value is it does give you some idea of why things dissolve the way they do. And was that my camera? Or was that your smartphone? Camera or smartphone?
Smartphone.
Okay. I recognize your voices, I recognize your beeps. So, I'm not going to do anything more with this. I guess I can take e to the each side and whatnot, or come up with some other approximation. I'm not really going to, but I just want to point out why do things dissolve, what makes things dissolve better, and point out how this equation is actually horrifically flawed. And that is what makes something, okay, let me do it this way. What lowers solubility? And again, now this one, folks, is really freaking hard to follow. So I'm going to do this real slow. Okay, now, the real thing that I have very difficult is to remember that when Chi-D is small, and let's call that bad, I'm adding salt to water because I want salt water. So I want this to be large. I want this to be as big as possible. Because why am I doing it otherwise? All right, so now again, this is going to go from 0 to 1, meaning that this is always positive or negative. All right, and this is always negative. And so here's the thing. Fusion temperatures, and again, that's when does NaCl melt. It's 800 K. I just looked it up right before class. It's like 802 K. This is gigantic. So, and I'm not going to ever, I don't have water at 800 K. That stuff boils, that's, 600 degrees, right? My water has long boiled off. So I'm never going to be working at the fusion temperature. I'm always going to be lower than that. Now, if that's the case, then this is 1 over a big number, which is a small number, and that is, that's going to be 1 over a smaller number is a bigger number, so this is negative. Now, by the way, fusion H's, they're always positive. You have to add heat to melt something. So that's always going to be true. Always positive, always negative, and it makes sense. It's the one thing that the equation does do right. Okay, now, remember, a bigger negative number is bad. That's the hard thing to get to wrap your head around. Bigger negative number means this is smaller. Remember, ln of 0 is minus infinity. And if it's 0, that means the material is not soluble at all. So what lower solubility will be a higher enthalpy of fusion per mole. I'm sorry, I forgot it was per mole. It doesn't matter. Sorry about that. Okay, now this kind of makes sense for a couple of reasons. For one, since this is always negative, this can only make it get bigger. If it gets bigger, this is a bigger negative number, meaning Chi-D is smaller. Right, and that's how you walk yourself through it, especially if I ask that on the test. And it also this is the one thing that does kind of make sense to me. The harder it is to melt something, the less soluble it will be. And that just kind of feels right. Another one is, let me get this straight. Let's see. It's a, oh God, what am I doing here? I believe it's a lower, let's see, all right, so I want this to be negative. I want this to be negative, so higher temperature that something melts at. Is that right? Yeah, that's right. So it kind of makes sense. Now this one, you just see that it's a bigger negative number. And this guy's more subtle. You actually have to plug numbers into this thing, and you'll find out that that's the case. Now, where is this horrifically wrong? Is one simple fact. Look what happens if T2 is T fusion. If that's the case, this is 0, and then that becomes, that's 1. That's right. Now that means, all right, so why is that way off? It says, as soon as something's hot enough to melt in a liquid, it's definitely going to mix with the liquid. Kind of. Now hold on, Chi-D is the mole fraction of B, and it becomes the number 1. That means, where's A? Where's liquid A? Where's the water? The water isn't there. It doesn't exist anymore. Now, that's wrong. I mean, well, maybe not in the case of NaCl because I've evaporated it, but that's not what's happening, all right? It's just a mistake. So again, this is critically flawed at higher temperatures because it just says as soon as something melts, that liquid solvent that I'm trying to calculate solubility in, that liquid doesn't even exist anymore, which is not even the question I'm trying to ask. So again, terribly, this is useful, but for the most part, terribly, terribly flawed. So, and I don't want to say much more about that. Let me introduce osmotic pressure and then just drop it. I don't think I'll put this on the test, but it is kind of important, and it could be under GRE. Some of you want to go to grad school, some of you want to go to med school. You really ought to go to grad school. You're not going to have a great job with just a chemistry degree. Too many people have chemistry degrees, so you're not special enough. So go to grad school. And this could be on the GRE. Okay, the way this works is we have a U-tube like this. And, sorry, I didn't quite draw it super well. I meant these to be even. All right, and then, salt water and regular water. Here. And this is an ion. Impermeable membrane. You can literally build this out of cell tissue, these ion impermeable membranes. So what happens is that it's like a Le Chatelier deal, that there's ions over here, NaCl, and the water is like trying to get rid of it. It's trying to get rid of it by diluting it. So H2O goes through. It's like a stress, right? The stress is the salt. The water doesn't like the salt, so the salt is going to just try to drown it. So the water tries to drown the salt. So it can move through this membrane, and again, it's kind of surprising how not hard it is to find membranes that are ion impermeable but let water through. It's kind of odd, but there's plenty of them that exist. And again, you can't actually use cell tissue to do this, to make these things. Now, the way that osmotic pressure works is that you have a different than height. Let me point out to you that, I looked this up right before class, 10.3 meters, a column of water that is 10.3 meters high exerts a pressure at the bottom of 1 atm. So to know the osmotic pressure, you just have to measure the height and then do the conversion, right? This will be like half an inch. So next up, come on, just 1 second. Let me just write down the equation for this. Just in case you see it on the test. Okay, instead of P for pressure, we're going to use pi for pressure. And that is going to be the number of moles of salt over V, which is the ion concentration. Okay, so anyway, I don't care too much about this. What you can, again, do is build one of these apparatuses, and these are actually kind of common because people do really, again, what you can do is you can put cells in here and make these measurements of pressure inside the cell by measuring this difference and knowing this. And that's all there is to say about it here. Pick up your homeworks if you haven't. For my office hours, if you have any questions, the homework is very easy.